Imagine you have a digital record of a 100 rupee transaction. Somewhere across the world, a stranger in Germany holds the exact same record. No bank approved it, no central authority verified it, yet both of you trust the ledger completely. That level of global trust relies on something you use every single day without thinking about it: a standard computer network. Grasping how a decentralized ledger operates requires an understanding of the physical infrastructure it sits on. To know how a blockchain works, you first have to know how computers talk to each other. In the early days of computing, machines were powerful but isolated. A computer could process complex data, but it had no way to share that work with the outside world. If a researcher wanted to share findings with a colleague in another building, they had to physically copy the data onto magnetic tapes, like this reel from 1973, and carry it over by hand. Buying one of these massive systems for every individual researcher was financially impossible. Operating localized tape drives required entire rooms and dedicated technicians, creating a desperate need for a way to log into the same resources from afar. The drive to eliminate that physical bottleneck and share hardware across distances led to the birth of the modern computer network. At its simplest, a network requires two or more computing devices, known as nodes. Every node is assigned a unique identity, ensuring data reaches the correct destination. Next, you need a communication link. This pathway connects the nodes via physical cable or wireless radio waves. When you transmit data, it does not travel as one giant block. The file fractures into tiny, uniform pieces called packets. These packets race across the link, snapping back together into the original file the millisecond they reach their destination. But the receiving node has to actually understand what those packets mean. This requires protocols, a strict set of agreed-upon rules that govern how data is formatted and processed. If two nodes attempt to communicate using different rules, the data becomes unreadable. Protocols ensure that the billions of messages traveling the internet actually arrive in a usable state. Networks scale to fit their environment. The smallest is a personal area network, or PAN. When you pair wireless earphones to your phone over Bluetooth, you create a network with a range of just a few meters. Step up one level, and you have a local area network, or LAN. In an office environment like this one, desktop computers are wired together to share a single internet connection and local files within one building. Cities link infrastructure through metropolitan area networks, and wide area networks connect devices across the globe. The internet is simply a wide area network connecting over 5 billion individual nodes. However, scaling to this level introduces friction. Massive open networks constantly expose data to malicious interception, and a single hardware failure can knock millions of users offline in an instant. Returning to that 100 rupee digital transaction, the trust between those two strangers is built on top of the network components we just explored. Blockchain is a distributed system. There is no central computer holding a master copy. Instead, thousands of independent nodes hold an identical ledger. To keep copies matched, nodes constantly fire packets across the internet, verifying transactions and maintaining consensus. Decentralization happens because a synchronized software layer is running directly on top of standard networking protocols. The physical network is the starting point for the entire digital world. In the next module, we look at the TCP/IP model. We will trace exactly how a packet of data descends through the internet, layer by layer, from the moment you hit send. Following that data packet as it moves through the model reveals the mechanics behind every global blockchain synchronization.